Very good evening to all. Warm greetings. Welcome to all for the another session of Friday Waters Thesis Club. The idea of Friday Waters is to wet the Fridays with fun-filled and yet fruitful activities for the future generations. Friday Waters has water talkies, book reading, thesis club, and water arts. The focus of Water Thesis Club is on bringing the student scholars who have done or are doing a thesis alias research on water matters to the session in order to discuss with them the making of thesis, research, and the issues around the subject covered. I am Ekta Gupta, the moderator for today's thesis clubs. I am joined by Dr. Mansi Balbhargav as a discussant for today's thesis club session. For today's session, we welcome Dr. Prashant Suresh Kumar to share his research on phosphate recovery from wastewater via reversible absorption. Dr. Prashant Suresh Kumar is passionate about reimagining higher education and research in India. He had a decade-long stint in Europe before joining Plaksha. He did his PhD from Delft University of Technology in the Netherlands in the field of water technology and wastewater treatment. His PhD project was part of very translational research atmosphere. The technology developed during this research was successfully piloted in Sweden and Canada to combat the challenge of harmful algae blooms. Post his PhD, he was involved in EU projects related to water technology and in science projects with high school students in the Netherlands, an activity he thoroughly enjoyed. At Plaksha, Prashant is keen to innovate on the teaching and research aspects involved in the technology education space. So now I welcome Dr. Prashant Suresh Kumar and I invite Dr. Mansi to take the session further. Over to you, Mansi.
Thank you so much. And thanks, Ekta, for first of all fishing out Prashant, because you have been doing very good work and diligently finding scholars across the country. So yes, thank you so much for that. And Prashant, it's such a wonderful occasion to really have you here, and also having met you before in Chandigarh event. And we really look forward to your talk. You will get around 25 to 30 minutes for the talk, and I'm prepared because you had shared your presentation. So really looking forward to it. A subject which is very, very crucial now in the world when we are dealing with serious wastewater problem. So we are looking forward to hearing from you, and then I'm going to pose some questions and we will take it further from there. Over to you, Prashant, and thank you so much for joining us.
Thank you so much, Dr. Mansi, and thank you so much, Ekta, for the invitation. I'm also looking really forward to interact with you on this topic. Can I share my screen? And
please go ahead.
Yeah, let me just quickly do that. Is it visible?
Visible. Please continue.
Fantastic. So I want to touch on my research for this, which was on my thesis, and I was doing this in the Netherlands. And you saw this institute, which you see here, WETSIS. So that's called WETSIS because it was in the Netherlands, and it was a special part of Netherlands called Friesland, where wet means water, sus is for sustainability. So it was a research center for water sustainability, technologies for a sustainable water solution. So that's what it was. And it was a very special time in the Netherlands. So I'll just set some context and get into the project. But I finished the project, in collaboration with Delft University, which is where I did my PhD. And ever since that, I've been involved in research projects which are more applied in nature. I've been involved in teaching. I've been involved in communicating science to different people, which includes students, the public, policymakers. I really enjoy interacting with them on the science part. And currently, I'm put up at Plaksha University, which is based in Mohali, as a faculty here. So during my time in the Netherlands, I just wanted to quickly post that Netherlands is famous for a lot of things. They have a very sporty culture. I myself am a runner. It's a known fact that it's the bicycle capital of the world. In fact, the joke goes that there are more cycles there than the number of people. You have very beautiful canals, and the subject of today's research is this, where you see canals with a lot of green layers, right? And that's what is eutrophication. That's a harmful algae bloom. So that was the topic of my PhD, how do we stop this algae bloom from happening? And it seems that the protagonist here, or the antagonist, depending on how you want to look at it, although I think of everything as a resource. So for me, this is the protagonist, is a phosphate molecule. And phosphate molecule is present in our body. It's there in our DNA. It's there in our bones, calcium phosphate, so we need it in our food. So here's what happens. We consume food, we take in phosphate. And of course, a lot of it gets assimilated, but some part of it is excreted. It goes to the sewage treatment plant. And from there, here it shows one green ball, which is one phosphate molecule, or let's say one, coming from one person, but you have such contaminants coming from a big municipality and ends up in the sewage plant. And then conventional treatment removes most of this, but there is still a little bit of phosphate left in the sewage effluent. And then when this is discharged into the water bodies, even the small amount that's there, that's enough to cause this algal bloom. That's enough to cause this eutrophication. So it's coming from us. We take it through food. It ends up in the sewage plant. Conventional treatment removes a majority of it, but a small amount that's left, that's enough to cause eutrophication. And this was a huge problem. That's a global problem, not just in the Netherlands. When I was doing my PhD, towards the end of it, I also got to work on this in different contexts in the world. One of them was in Florida. So they had a huge challenge with this, and they had to declare an emergency due to toxic algae that was coming in. So they threw up a challenge. And this is very important. I want to put it out there for researchers, because sometimes you do a lot of research in the lab and you wish it gets applied in the real world. But to catalyze that translation, from the lab to the real world, sometimes you need incentives. Sometimes you need a pull as much as you're willing to push. And this was one such incentive. There was a water prize announced by, an organization in Florida, and they said, this is the biggest water prize at that point of time. It's a $10 million prize. And they said, we invite people from all over the world to come and solve this problem of harmful algal blooms we have. So that's what we did. And there were two main challenges. The award was not an easy piece of cake. Two main challenges. One is you have to reduce the concentrations to very low levels, 10 micrograms of phosphorus per liter. So you have to reduce that. So you need to have a technology that can do that. And then there is an economical challenge, which was that, per kg of phosphorus you remove, the cost should not go more than $100. So these two criteria we had to fulfill. So we participated. It was really nice because it was mimicking how a process, scales up or comes out of the lab. So first you give an ideation, then you show it on the lab scale, then you do it on the pilot scale, and then you do it on the full scale. And so me and my team, I have to say, it was really a teamwork. We went through all the way to the pilot phase. We were the winners in all the stages up to that. Of course, after that, COVID happened, and amidst other things, we couldn't get forward, but we put the idea forth. That was very important for us. So let's get back to the problem to understand how big of a challenge this is. When someone says 10 micrograms phosphorus per liter, right, to stop the algal bloom, the concentration needs to be less than 10 micrograms per liter. Just to give you an understanding what that means, if you take a cup of tea, in Europe, it's pretty normal to have this, what I call hot water with some color. So that's very different than, having the milk tea that we have here. But anyway, let's say if you want to add some sugar in that, right? So you add a couple of teaspoons of sugar in there, and then you taste the sugar, you taste the sweet flavor. Imagine you take that amount of sugar and put it in, 1,000 cubic meters of water, right? I want you to think, would you be able to taste anything? That's the level of concentration we are talking in terms of phosphorus. If you were to take 2 teaspoons of phosphorus and put it in a huge Olympic swimming pool, would you be even able to detect it? So already detection is a challenge, but that concentration is enough to cause algal bloom. So that was one of the challenges. So, the other thing is phosphorus is, like I said, is not just a waste. It is required in our food. So we wanted to take the phosphorus out of the place where it's a pollutant, which is the sewage effluent, which ends up in the river, and convert it to a useful resource, which would be something like a fertilizer, a raw material for phosphate fertilizers, right? And so inspired from I was also mentoring young students there. So I used to get a lot of inspiration from them, how to communicate this. So essentially, we were looking at something like a phosphate transporter. So our technology was all about transporting phosphate from the sewage and, bring it out to a place where it can be used as a fertilizer. That's sort of, the layman's point, analogy for it. So it's just a transporter, and it's got a lot of similarities. So you transport it from a place of pollutant to a place where it's needed. And this technology that we used for it is reversible adsorption. And we call it reversible because we want to remove it, but we also want to take it out and recover it. So that's why the process needs to be reversible. So let's look at the similarities in terms of transport. So your human body, the Dutch people are very tall, but on average, it's about 1.7 meters, the height. A phosphate molecule is extremely small. It's about 0.5 nanometers. That's the size of a phosphate molecules. But the transport facilities are similar, except that just like we design a transport vehicle for a human, you have to design a vehicle for phosphate, transporting phosphate. And it's of course very small, but similar principles will apply, as you will see. So if you think about a transport, right? Let's say if you are the guy who's giving out a transport vehicle, what is it that you will be thinking when you build a vehicle like that? I put in this picture because KLM is a very famous Dutch airline. So when you think about how you will develop a vehicle, you think about important parameters. One is how many seats does it have, right? So what is the capacity? How many people can it transport from one place to another at a single time? Similar to that, we want a phosphate transporter, that can bind as much phosphate as possible and bring it out. How fast can you do? As you know, time is money, time is very important. So the speed of the process is very important. Lifetime. So let's say if you buy a car, you don't want to buy it just for a few times use, right? You want to buy it for a long time so that you can keep using it. And that will eventually bring down the cost of the whole process. So these were the parameters we were looking at. And I'm going to focus on few of these parameters going forward. But this is just to set the context. Essentially, we are developing a technology that can transport phosphate from a place where it's a pollutant to a place where it's a resource. And we are looking at some of these parameters that would apply for even a transport of, the normal public. So the first point was the material we use to remove the phosphate, that's called an adsorbent. How do we choose one? So, what are the characteristics we have to look? So one is it should bind phosphate with high affinity, which means even if there are other ions in there, it should show some sort of selectivity for phosphate, so that it can pick phosphate out from the water, but it should still be reversible. Because like I said, we just don't want to bind the phosphate and dispose it. We want to get it out. We want to recover the phosphate and reuse it as a fertilizer. So that is one. The second is it has to remove a lot of phosphate at the same time, so that the treatment speed and the treatment efficiency could be better. So we looked at nature, and I myself, as a child, used to collect rocks, much to the bemusement of my family. They were not always in favor of it, but when I look at these minerals, all of them have iron and phosphorus in common. So by nature, you can already get some inspiration that, okay, iron and phosphorus have some affinity for each other. And all these minerals have iron phosphorus, composition in them. So that is one. That was already a clue that, we could look at something that has iron in that. The second was we were looking at what were the, in research, what were the adsorbents being used. So there were three main players that came out. One was aluminum oxide. The second was iron oxide, so basically rust. And the third was lanthanum oxide. Lanthanum is slightly a rare earth metal. And aluminum oxide had a moderate binding. It was very cheap, but there were toxicity issues if the aluminum dissolves in water. Iron oxide showed good binding. It was cheap and it was not toxic. Lanthanum oxide had a very high binding. It was more expensive than iron or aluminum, and it was not toxic as well. So based on this preliminary comparison, we decided we want to go with iron because aluminum had toxicity issues, plus the binding was moderate. Lanthanum was slightly expensive, and also the binding was so strong that it would be very difficult to get the phosphorus out of it again. You need to use some really harsh conditions to get the phosphorus. So that was a no, it was not the best transport vehicle we were thinking. So for us, iron was the thing. Iron was the one. Iron was, let's say, the chosen one. And now if you look at iron, if you look at the granule of iron oxide, so when we first identified the properties, you can see the slide, right, Mansi?
Yes.
So when we first identified the properties, one of the first properties we wanted to work for removal of phosphate is the capacity. How much phosphorus can we bind per gram of the material? And adsorption, we decided iron oxide is a good candidate. And adsorption usually is a surface phenomenon. And you see this dark brown is where the adsorption happens. which means everything that's in the bulk is a waste. So we needed to have something with a higher surface area. So one way to do that is to break it open. And once you break it open, all these green highlights that you see are additional surface area that become accessible. And we see this in our everyday life as well. For instance, when we chop vegetables, it cooks faster, right? So you basically have a higher specific area to the volume ratio. So similar idea. So we break down the adsorbent and the area is higher, which means it can bind more. The challenge is if you grind it too small, then you have what is essentially a powder. And then, when a powder is put in water, it's very hard to recover it back. There are some operational problems like, high pressure drop if you run it in a column. So putting something that's very powderish is also not an option. So what we did is let's use some supports. So you break down the iron oxide. So you have it in very small sizes. And then you use a support material or a backbone where you can put these small particles on the support material. And the support material could be a wooden chip, could be activated carbon, could be proteins as well. So the idea is overall the particle is still big, but on it, the disposition of the iron oxide has been done in a way where the area is high. So here I just want to take a detour and talk about adsorbents and, what I call surrealistic surface areas. If you have a look at some of the objects we have here, we have a Rubik's Cube, which has an area, roughly about 150 centimeters square, and it weighs about 25 grams if it's a plastic one. A human being, like I said, in the Netherlands, they were a bit taller. So about 1.8 meters square would be their area, and they would weigh about 70 kilograms. If you look at this truck, it would, have an area of about few hundred meters square, and it would weigh about a ton, maybe even more. But if you look at this guy here, the activated carbon, if you want to take a guess, and I think you would know, Mansi, about this, is that it has a very huge surface area. It has an area of about 1,000 meter, greater than 1,000 meters square per gram. So when the first time I saw this, I was like, no way this is possible. And then I thought, okay, if it's possible, then I should be able to explain it. I have to first convince myself, then I have to, explain it to others. So this is what I did. So let's say, you take a cube. I mean, here it's just a representation in a 2D, but let's say you take a cube that's 1 centimeter by 1 centimeter in size. And for simplicity, let's just take the top as the area, right? So this top has an area of about 1 centimeter square. If we just take, for a simplicity, just the top of the cube as in surface area, that's about a centimeter square, right? It's just a cube of 1 centimeter size. So now let's take the cube and make it porous in such a way that there are 3 layers: a top layer, a middle layer, and a bottom layer, right? So what you'll have here, again, just assuming the areas of the layers, you have about 3 centimeters square is the surface area, but then the gap between the 2 layers is about half a centimeter. So the total surface would be about 3 centimeters square. Similarly, if you make it porous, if you have 4 layers, then you have 4 times 1 centimeter square, and then you have a size between about 1/3 of a centimeter. So the surface area would be about 4 centimeters square, right? You got the idea. Now imagine this: you take this cube and you make 10 million lines out of this, right? Of course, it's very hard to visualize in a slide, so you would assume this is 10 million. Then you have a surface area that's 10 to the power 7 centimeters square, which is about 1,000 meters square exactly. And then you can say, hey, but the layers between these, the gap between these layers would be extremely small, in which case you would be right. This would be about, a few nanometers, but that nanometer is enough for phosphate molecules. It is good enough for the size of a molecule. As an analogy, you have this tallest building. I think it's the Burj Khalifa, and so it's about, what is it, Mansi? A few 100 meters square, closer to a kilometer, I think, but way bigger than the Eiffel Tower. Imagine, so this is about, I think, 200 floors. Imagine this building had 10 million floors, right? And if in all the floors human beings were walking around, that's exactly how phosphate molecules would be zipping past in this activated carbon, because the layers are so thin, but they're big enough for phosphate molecules. But since you have so many layers, the pores are intricate in such a way, you have such a huge surface area that's possible. So that's what we used. We used a granular activated carbon. We took a small amount of iron oxide, and we basically coated this iron oxide into the activated carbon. So essentially, you still have a particle that's sizable, but it's very porous. And because of this pores, you can put nano layers of iron inside there. And then this is having a very high surface area. And as a result, you can bind a lot more phosphate, right? So if you were to zoom in and look a bit at the process, if we zoom in a little bit, you see this is how the iron hydroxide is layered on the carbon. So when you have phosphate polluted water coming in, so we have a process called ligand exchange. So the phosphate comes in and it binds and it kicks out these surface hydroxyl groups, and it binds to the iron layers. And this is the mechanism of removal. And if you want to reuse, if you want to reverse the process, you just bring in a lot more OH ions. You just increase the concentration of OH, and then the driving force is good enough that now these OH can kick out the phosphate. So now you can kick out the phosphate in a concentrated form from where you can recover it. And then the iron hydroxide is also replenished, right? So that was the story. There was more challenge to this. And one of the challenges was it was not very easy to coat an activated carbon completely with iron oxide because the pores were very, very different in size. So you had very small pores, and you had big pores, mesopores and macropores, and the very small pores you couldn't coat with iron oxide because they were too small, less than 2 nanometers. So what we did is we took this rust, which is what we call as iron oxide, right? And we want to improve the capacity. So if you think about it in the analogy of a vehicle, you want to increase the number of seats, right? So basically, if you want to improve the capacity, you can increase the number of seats. So instead of putting iron oxide onto carbon, what we essentially did is we made the iron oxide, here you see the char is just on the surface, but if you make the iron oxide porous, then the char is all around in the pores. So it's like using a cloth to scrub away a dirt versus using a sponge, which is very high in surface area because it's got a lot of pores. So this was one part of the deal, so porous iron oxides was what we used in the end. And then the second part of the deal, so with this we could achieve those low concentrations. The second part of the deal, as you remember, would be the cost. Essentially, it was something like this. 100 euros is not shown, but it had to be less than $100 per kilogram of phosphorus treated. And you could say per kilogram of phosphorus doesn't seem like a lot, but remember the Olympic swimming pool analogy I gave, the concentrations are so dilute. That means to get to 1 kilogram of phosphorus, you have to process several, thousands of liters of water to get that amount of phosphorus out. So it was actually pretty expensive. And the only way we think it could be economically feasible is to reuse it. So essentially, like the example I gave with the vehicle, if you want to buy your own vehicle, you don't want to buy it just for a few times. You want to do it for a whole lifetime. So the idea was, just like you refuel your phosphate transport vehicle, in a similar way, you want to replenish the sites on that sorbent. And there was one final challenge. How are we doing on time, Mansi? Do I have 5 more minutes to wrap this?
Please take your time. You do have. Yeah.
So then I'll just wrap this reuse part. So what we realized when we put it in, clean water, we could just bind the water. So, in research, we first tested on clean solutions before we go to more complicated solutions. In clean solutions, we could put some chemical, just like the hydroxide, and kick out the phosphorus and recover it. But in a real wastewater matrix, this was a big challenge because in the real wastewater matrix, there are a lot more ions that are present. And what we saw was we saw these white things forming on the adsorbent. When we looked at it under a microscope, we saw these white sort of precipitates. And this was very similar to the precipitate. When we analyzed the chemical composition, it's very similar to the precipitate or the scaling you see in our bathrooms, you see in this boiler. So it's basically calcium carbonate. So we saw that the iron oxide binds a lot of calcium carbonate, and that, blocks the adsorbent surface. So just like you clean your kitchen appliance with some vinegar, some slightly acidic solution, use a small concentration of acid, it cleaned the calcium carbonate precipitates, and then, we could reuse it. And so that was what we did. We made sure we remove the scales on that adsorbent, and then we do the desorption process to reuse the material. Where is this applicable in a real scenario, this technology? So that was the idea of the technology, that, we developed an adsorbent where we could remove a lot of phosphorus, and we also developed a strategy to reuse the adsorbent, and recover the phosphorus. If you look at a conventional treatment plant, you have multiple steps for removing nitrogen and phosphorus. Some sludge is formed from which you form biogas. And, the phosphorus, if it's present just in the sludge, it's wasted. And there are some research going on in that direction to recover the phosphorus. Adsorption could come, in a tertiary step where you want to polish the phosphorus and really go down to the trace levels and recover the phosphorus. So that's how it fits into the wastewater scheme. So because then we are targeting very low concentrations. This is just, I think, the final couple of slides. What I want to tell is a message on multidisciplinarity. So this project, of course, I say it's a water technology project, but when I look back at my office, I had all my colleagues. One was, a biologist, one was a chemist, one was a physicist, one was a coding guy, one was a mathematician. So we all used to exchange ideas. And the director from my former institute used to call that, complex problems. He said, can't be solved by a single discipline. You need something called the multidisciplinarity magic. You need to brainstorm with people from other disciplines, and then you will see ideas converging. And that's how you solve grand challenges. And I had a lot of examples like that in my project as well. A lot of it required chemistry. We were looking at biological options. A lot of mathematical modeling was required in the process. So it was a coming together of different streams. So as a conclusion, like I said, I'm not looking at phosphate as a waste. And I think it is the same for any other component, which is a contaminant, because it is a contaminant in the first place because it was being used, which means it has some use somewhere, right? So waste can be a resource as well. So there are two sides of the same coin, is what I want to say here. Multidisciplinarity research is much needed to solve complex problems. And, whenever we do some research, of course, the technology is what researchers conventionally look at, how well it performs. But, to bring it out of the lab and take it out in the real world, it is very important that the research is economically feasible. So that needs to go hand in hand with the research as well. I think with that, I will stop my conclusion. Apologies for the delay due to the interruption of the internet.
Thank you so much, Prashant, for a very interesting, even though it was highly technical, but you really made the presentation look so simple. But I know that it is not as simple as you made it sound to us. And when you were giving the example of presence of phosphorus with Burj Khalifa, that time itself, I was imagining the seriousness of its presence in the water. But you also concluded it in very nice way that if this contaminant is found in the water as a contaminant, means it has been used for something, which also reflects that it can be reused as well. So thank you so much for putting it in a nice way where you say that phosphorus is not a waste, or it is not making the water waste, but it is a wealth which we can think about. And you really gave very simple examples of it. With giving transportation as example and other things, and especially seeing that it is going to be naive to treat phosphorus and make the water pure. So better to look at it from a reuse perspective, because anyway it had a pre-life. So right. One can think about the post-life of phosphorus as well. So that's the scientific part of it, but emotional part of it is thank you so much for making us and especially me to travel through Netherlands through your presentation, looking at those canals, the green and the clean canals.
Thank you.
And cycling together. So we have more bonds to share from Netherlands, because I think those who have studied in Netherlands, water connects us because you cannot escape studying water. So good to know that your links with Delft and my links with Erasmus Rotterdam also will go a long way in the way we look at our future collaborations in the water sector. Now, coming to some questions which I have from your presentation, I will go through your slides presentation, but may I request you to switch off your presentation so that we can really have just one-to-one conversation with each other. Sure. So my first question to you comes as when you're talking about you looking at phosphate or its allies. Let's say you did talk about its relation with iron. You did talk about hydroxide. You did talk about calcium carbonate and other things. You were talking about both sides of its use. I need to understand from you in the Netherlands context, and I would like to draw your attention and also get some reflection in the Indian context here, because we are also first, diseased by its contamination. So coming to the Netherlands, so if we have to enlighten the younger generation about its pre-use before it is considered as a contaminant, and what kind of reuse you are envisaging post it is declared as a contaminant, and when innovation, like one you mentioned that it is the innovation is involved in it. So over to you.
Yeah, thanks. So, in terms of reuse, I think the seriousness of the situation is, of course, here we are talking about water, but I'm sure, Dr. Mansi, you're aware of, this food, water, energy nexus, right? And phosphorus is a clear example where it's, of course, a pollutant in water. It can cause huge algal blooms, but it's also a concern for food security, if it's not
Yes.
there in the
Yes.
crops, right? So it's a fertilizer. So we are looking at global food shortage if phosphorus is not there, because as
Yes.
simple
We
as
need it. We
Yes.
need it. In
we
short,
need it. There is no way getting around. It's a micronutrient, but still, it's like I said, it's there in the
how
body.
much? It's how much? It's just like salinity, I mean,
Yeah.
you can have this percentage, not more than that, but
Right.
not less than that is also not going to work.
Exactly. So you need just the right amount, but you need it.
You need it.
So it is a concern, and one way to look at it is, it's not just about water. Water is, of course, also the topic here, but it is a food. It's a requirement in the food. It's a requirement in the fertilizers. I'm sure, as you know, nitrogen, phosphorus, potassium fertilizers,
Yes.
they require phosphorus. And in the Netherlands and in a lot of European countries, this was becoming a geopolitical issue as well, because they usually conventionally use phosphate rocks for making the fertilizers.
Yes.
Countries are running out of phosphate, and mostly they import phosphorus rocks from Morocco, or China is a big supplier as well. But so they also realize in the Netherlands, even if the water pollution side of it less compared to, let's say, a developing country, they realize that if they don't recover the phosphorus, and just they discharge it in the surface, and then whatever happens, if they let it like that, at some point they will run out of the food security. So they more and more are looking at secondary sources for recovering phosphorus. One of them is wastewater. So I think there the main focus would be reusing the phosphorus as a raw material for the fertilizer. In India, it's very interesting. When I spoke with my VC before coming to Laksha, the challenges are very different.
Yes.
Eutrophication is, and in the technology I was looking is more at the tertiary step. It's at the pipeline, end of the pipeline.
End of the pipeline.
Whereas in India, even the basic, I mean, it's challenging, and I'm not saying we are here to solve it, of course, but the challenge is different here. The challenge is there is a lack of, in many places, that's the honest review. I mean, even though it doesn't feel so nice, there are reports on this by the Central Pollution Control Board, and about is not being treated adequately. So forget that phosphorus is, the dilute concentration I'm thinking are coming later, but the basic sewage is not getting treated. So the challenges are very different here. That's not to say that, we should not recover phosphorus, but we need to think of technologies that come a bit earlier in the pipeline, and eventually if we refine it anyway, it can go into the fertilizer part of it, because that's where we need it a lot. But it needs to come a bit earlier in the pipeline. That's how the situations are different in both the economies.
So just to get a little bit more clarification, that in India, are we realizing its importance just like in Europe? Because we know that the whole geopolitics of Europe is, and especially if we talk about Netherlands and Belgium and other places, nearby countries, they actually need phosphorus for their,
right,
in a way. Yes.
Right.
But what is our status in India? Are we realizing its importance, or we are complacent with its presence? Because we don't have to import, actually. We are not importing it, right?
Correct. So we are.
That also makes us, bit of, I should not use the word lethargic, but ignorant, or it's not an urgent issue, complacent. I mean, complacent is a better word.
Yeah.
What's your take on that?
That's a very fair point. We have a bigger reserve than most of the European countries. So that could make us a bit, indeed, like you said,
rich. We are rich.
We are rich in that for a change, right? That's good.
But it's a devil. when we talk about wastewater, we consider it as a devil. I mean, along with phosphorus, the nitrogen. These are the two things we are trying to fight out when we talk about wastewater treatment.
Right.
Major two things.
Right. So you're right. So here we are still at a stage where we are mostly looking at it from a pollutant removal perspective.
Yes.
The recovery is not at that mark. That's
Recovery
not
and reuse.
recovery and reuse.
And reuse is
That's
not discussed.
Exactly. That's not to say that research is not happening. There are some really good institutes where research level that's happening. But at an implementation stage, I think not a lot has unfortunately happened yet. But I do believe we are headed to a time where, push will come to a shove, and then we don't, I mean, then it's no longer a matter of choice. I think we will have to be a bit more stringent. So the technologies are there. Can we make them more feasible? Certainly some research can go in bringing making them more economically feasible. The technologies are there. A lot of research has been happening, but there is there is not enough drive to implement it, I would say.
Yes.
Which has been a challenge with a lot of topics here. But like I said, I think the time it's pretty soon getting to a time
On the
where
corner.
yeah, we are. Yeah, exactly. So it's no longer a choice. I think it will become obligatory. Yeah.
That's interesting to know. And when we talk about these kind of research, I have no doubts that we have some of the advanced research is happening here. And it looks outdated in the terms that these are advanced researches, because our policymakers and decision makers are somehow weakly empowered about this kind of knowledge. So when we are talking about wastewater treatment, and when you look through the DRPs or the reports or the project reports, you really don't see these, be given attention or, due respect, as I was using the word devil, because the whole focus is on how to get rid of it. But get rid to where? That is also something which one has to discuss. Right. So I need to understand from you about, and you had very interestingly presented its relation with human body, and also you were trying to explain with an analogy about its flow. So I would like to really get ourselves enlightened, because for me this is also a new subject. So I'm curious. And pardon me for being that Rex with lot of naive question, but that's my task.
No. I mean, that's where some of the most significant learnings happen. I think when
I'm reflecting a society, Yeah.
So I wouldn't call it a naive question. I would call it a question from a different perspective. So
yes,
we really need those
layperson question. So I would like to understand if it is an important component in the food chain, right? So we have to understand a deficiency of phosphorus means what to human being. Maybe that can be one of the defending arguments to start looking at reuse of phosphorus in our food in India. And because we know, both of us know, and many people know, that Netherlands is investing heavily in nature-based solutions and wastewater treatment as an international agreement between India and Netherlands, and their major knowledge exchange is on major wastewater treatment. And I'm sure we are having a lot of transfer of technology and knowledge and exchange. So food in Netherlands and food in India, where do you see the deficiency or sufficiency really plays a role? Because that can be a game changer in India as well, when we start looking for perception change or preference change.
Right. I think the bottom line, of course, is that without phosphorus, we simply cannot exist, because it is there in our composition. We are talking about, let's say if there is not enough phosphorus, then we can think about, what sort of diseases might be there, bone densities, osteoporosis, those challenges will happen. But the bottom line is, it will quickly come to a stage where we cannot survive anymore, if it's a continuous deficiency in the diet. It is an essential component of the DNA as well, the sugar phosphate backbone. So there is no going around it, Mansi, that
no room for pushing around.
No room for pushing around. So because if you think about it, except for the refined food, this was a very interesting question. I have to share it with you. When I was presenting to school students, and I was telling about, phosphorus, where is it there? It's there in the food. He brought me a box of Pringles, that potato chips, right?
Yes.
And he very innocently came, he showed me the box of Pringles. And he said, "Sir, does this potato chips also have phosphorus?" I asked him, "What do you think?" He said, "Sir, I think it might have." I said, you're right, because what is potato made of? Potato is also vegetable. It also has cells, and every cell has phosphorus. So there is no simply getting away around the fact that, any food we take, unless it's a highly refined food, it is bound to have phosphorus, because without phosphorus, there is no life. It's not just for humans, it's for all organisms. Phosphorus is the backbone of, every cell. You would know about, one is DNA, the other is what they call adenosine triphosphate. It's an energy currency in the body that has phosphorus as well. So any vegetable, any food, any organics, any meat, any live product you consume, any product that's not refined, let's put it that way, it is bound to have phosphorus. If it's deficient in phosphorus, first of all, the food would not be good. Second is we will have a very small window before we, struggle for, even performing the basic functions. So it's simply not a choice. It's got to be there.
Yes, again, asking a naive question for our, as a citizen science, where is phosphorus in our body? I mean,
Yeah.
where do they flow, or where do they live? So that we know we can deal with them or treat them with more respect than we do today.
Right. Dr. Mansi, you have a very good smile. It's right there in our teeth to start with.
Okay.
Calcium phosphate.
It was a clue to you.
Yeah, thank you. It's there. So calcium phosphate is there in our teeth. It's there in our bones, calcium phosphate. And every cell in our body, which has a DNA, I will give you a few examples. Every cell is covered with a membrane, a cell membrane. That has something called phospholipids. It's what protects the cell from, whatever things are coming and going out of the cell. It's a barrier to the cell. It's a cell membrane. That membrane is having phosphorus. If you go a little bit further, then you have this molecule ATP, adenosine triphosphate. That's there in all the cells. So whenever we eat food, whenever we get energy, we talk about glucose, we talk about, glycemic index, but ultimately it all gets converted to ATP. There is this molecule adenosine triphosphate. Whatever food you take, whatever sugar, glucose, fructose, carbohydrates, ultimately the currency that it's converted to energy currency is adenosine triphosphate. Again, that is the phosphate molecule. And then if you go deep down into the nucleus, the DNA, or deoxyribonucleic acid, which is the genetic material in our body, it has phosphate, sugar phosphate backbones. So without phosphorus, first of all, no bones, no teeth, and then no
smiles
cells.
Also. Thank you so much. No smiles as well.
Exactly, no smiles, and that is at the outer level. At the inner level, there won't be any cell membrane, which means you will be, you won't be able to survive, because the cell membrane is what protects each cell, from the entry and exit of required compounds. And then if you go a bit deeper, we need ATP for energy transport. And then if you go down even deeper, the very deep of our genetic material, very fundamental molecule DNA, that also will not be there without phosphorus. Yeah. So that's one of the reasons, Mansi, you might have heard that arsenic is very poisonous.
Yes.
And one of the reasons is the structure of arsenate, an oxygenated form of arsenic, is very similar to phosphorus, because phosphorus and arsenic are very close by in the periodic table. So they share very similar chemical properties. And one of the reasons arsenic is so poisonous is because it binds in our body and it sometimes replaces the phosphorus, it displaces it rather. And then, our body can't function anymore normally. That's why you can already see a small level of arsenic, which means a small level of phosphorus being kicked out, is already very toxic for us. So that's also in a way connecting to your previous question, what it means if we don't have a little bit of phosphorus.
Very interesting. Let me just return to some more questions from your presentation itself, because we started talking about putting some coating and, and how it's there in the cell and all. You did talk about some supports, and you were giving some interesting examples from protein as support, or activated carbon and wooden chips. And just before that, you were also talking about the surface area, where you gave those shocking numbers, when you talked about the activated carbon and the phosphate or phosphorus around it. I need to understand from you, when you were talking about decomposing it into smaller granules and then talking about coating them, what exactly does it do to the whole system?
So when you break it down just like that without using any support, it becomes
Is it-
very powderish.
Sorry, let me just add a little bit, because the moment you said break it down, I could realize, because you had showed two, samples, or let's say two classification in terms of granules and powder, and
Hmm.
it is about the size. So please
Yes.
continue. Yeah.
Right. So we had granules and powders. If you use granules, right? So basically, the granules were a few millimeters to a few centimeters in size. They're easier to handle. You know, we can imagine any sort of, let's say, if you spill something while you're cooking, right? A lot of times, chemistry, as you know, is similar to cooking. If you spill something while you're cooking, and it falls in the water or something. So if you have particles that are bigger in size, you can easily separate them out. Whereas if it's very, very small, it becomes very hard to, separate them out.
Right.
So if you have granules, it's easier to handle them. But then the surface area is very small. The surface
Mhm.
area per volume is very small. The specific surface area per mass as well. Whereas if you have powder, when you grind something, the surface area becomes very
Much
high and the
larger.
reactivity increases, which is why a lot of inert elements, even like something like a gold, which is very inert, which doesn't react when you wear it as a necklace. If you go to the nanoparticle size, gold becomes very reactive. One of the reasons is the specific surface area is very high and suddenly the reactivity increases. So in a similar way, when you powder this, the reactivity increases because the area is high. But then, like I said, the challenge is to work with powders is very messy. If there is a spillage happening, it's very hard to recover it. If you want to pack it up in a column, it's a powder and becomes, when liquid flows through it, it becomes compressed. And then you have a huge back pressure developing, which means the flow will get a lot of resistance. You won't be able to make it flow. So to overcome that, what we did is we chose granules, which were porous like carbon. So these were porous enough that, and they were big enough that they were in the millimeter to centimeter size. So they were easier to handle as a particle. But because they had pores, we could use these pores to coat iron oxide inside these pores. And so it meant the overall particle size was big enough. And the pores, since they are pretty diverse and the area is very high, the reactivity after the coating is also very high. So that's how we got the best of both the worlds. Let's put it that way.
Interesting. I mean, my questions are going reverse, because that was easier for me to understand and go
Sure.
reverse of your presentation.
Yeah.
So I'm coming to those interesting, stone-like minerals which you were showing, very glitterati. And
Right.
you also related it with in the childhood when we used to find them. I recall collecting a lot of this mica from this seashores and all, or river bed, because they used to shine,
Right.
and just stick it on our dresses and everything like that. So when you were showing these minerals, and now when you talked about the particle size and all, I'm just getting curious when phosphate is on trade. Let's say in Europe, as you mentioned, in Netherlands, they are also getting phosphate from Morocco and other Arabic countries where it is available. What kind of pricing goes on, so that we can also start looking at it from its commerce perspective? Maybe our waste recyclers will look at it more lucrative to recover phosphate, because we are barely doing wastewater treatment at this moment in the country, because it's a pain for us. But once we start looking at lucrative resources recovered from waste treatment, probably there are more takers. It's just like solid waste treatment. If you have those reuse, recycle, upcycling products, then there are more takers. But there are not many takers, or there is not enough market in wastewater yet as it should be. I may be wrong to some extent, but if there are markets, we would have really good wastewater treatment systems. The way our wastewaters are struggling. So I just need to understand what kind of pricing goes in the phosphate trading when it is used. And you use the word nutrient to contaminant or pollutant, something like this, and where you're talking about pollutant to nutrient again, right? So what is the trading and how the trade happens in this arena?
That's a very good question, and it's a very important question. I might not have the latest numbers, but when I was still in the Netherlands here, so the cost of phosphate rock, if I remember, of course, there were fluctuations in the price. I think somewhere in the mid 2000s, the price shot by a factor 5 because of this geopolitics issue.
Yes.
And then it came down a little bit. So it was a few thousands per ton of phosphate. So that was about
Okay.
a couple of euros per kilogram of phosphorus,
Mhm.
which in INR would come out about $200 per kilogram of phosphorus. That was what I recollect. And
That was many years ago.
it was, yeah, 5 years ago, around that. So it would have,
Uh.
of course, increased now. But this is a crucial question, because I think we have to get to the bottom of this. Sometimes it could be that the cost of the product you recover might not be high enough. So 200 rupees per kg is not very low. It's not very high as well.
Yeah, but it's not the only product you are going to recover. It's one of
Exactly.
the products.
It's one of the products. And that's a very key, that's a crucial point. And the second is the economics of just the recovered product might not be enough in some cases. Like in this case, if people are able to, it's a little bit like the water situation in Punjab. We can say that, hey, let's please conserve water, let's treat the wastewater and reuse it. But if the cost of wastewater treatment is high, farmers would rather, just dig their bore wells and, take water from underground.
Which is very easy. And that's why we are the largest waste groundwater extractor in the world, 70% groundwater extractor of the world.
Which is so sad in a sense. And that's also because, electricity is being, there's so many, it's a complex, yeah.
Yes.
So in a similar way, if you purely look at the incentive of phosphorus recovery in this perspective, it might not yet be at a point where we are tipping off the treatment cost. But like you said, there are other things you recover. And second is, we shouldn't look just as the cost of the recovered product, but also the savings you make, which is a harder thing to measure in terms of preventing pollution, right?
Absolutely. That has to be factored,
That has to be factored. Because the reason they threw up this challenge which I showed in the slide is they saw a huge problem with the toxic algae in Florida. And it was not just a toxicity concern. As you can imagine, if the water bodies become very green and polluted, people can't swim anymore. It's toxic. So it affects the, recreational industry. It affects the fishing industry. Fishes die. It affects the tourism industry. It affects the real estate industry. Nobody would want to buy a property there. So the government is looking at $1 billion loss here because of this problem. So you need to combine both of these aspects when you look at the overall.
And then factor it. Then actually it's not, because what you were talking about is its net present, value. But if you factor all these things, but the gross value may be much higher than one is looking at. And probably it's a value which many stakeholders will have a share to it.
Right.
I just feel like going on and on because it's a very new subject for me. So I really wish to dig further. But Ekta may be looking at the timeline of the session. So Ekta, what do you suggest? One last question, or we can wind up? Or you have questions?
I think we are here for the discussion. Then we should not leave anything in between.
Okay. So do you have any question, or I wish to ask one last question?
Yeah. I have to connect with the battery. So give me a moment. You just continue. I will.
Okay. Thank you. So my last question is actually from your first part of your presentation. As I mentioned, I'm going reverse. So when we talk about eutrophication, and you also showed the canals of Netherlands. And when we look at our lakes and drains here, we don't call them canals. We have drains. Right. When we look at them, we have very different situation, even in terms of pollution in both places, But let's say my question is focused more to the Netherlands, So if we look at eutrophication in Netherlands, is it a kind of a cyclic process that they are already having quite a bit of phosphate and nitrogen content, which is nutrient to pollutant, as you mentioned in your presentation? What is the reason that many canals, or is it because those canals get landlocked and they are short of aeration, and that is why they get, because if there is aeration happening, actually eutrophication can be handled very easily. So what is the role of, you did mention on, oxidation a little bit. What is the role of oxygen, or you use the word hydroxide, in keeping eutrophication at bay? And does it mean that no eutrophication means that the phosphate level in the water is decent?
That's a very fair question as well. Eutrophication is one of the indicators that the phosphate level is decent in
Oh,
the
it's an indicator that it's a decent phosphate level with
if
eutrophication.
eutrophication is not there,
Is not there. Okay, so
absence of
my understanding,
absence
yes,
of eutrophication.
yes, of course, yes,
So it can be used as an indicator.
yes,
It's not an all exclusive thing. First, I will get back to the oxygen part of it because oxygen, depends on the treatment you're looking at. Oxygenation could be useful, but
yes,
oxygen levels do deplete once the algal bloom has set in, as you would know,
yes,
because
yes.
they consume the oxygen.
Nothing is goes in and out. So
Yeah, exactly. And when they decompose, that decomposition consumes oxygen, and then this suffocates the fishes and all the other aquatic organisms, so they die. Can eutrophication or an absence of it be used as an indication? Yes. It's not a guarantee because it's very beautiful. The chemistry is one is there is soluble phosphorus, which the algae can use.
okay.
But the
Hmm.
phosphorus can also
We
be
call it good for, shall we call it good phosphorus?
good for the algae. Let's put it that way. So it still has to be kept in check. And then there is this particulate phosphorus, which is phosphorus that's bound to some solid, could be some adsorbent, could be organics. It's in suspended form. It's not really dissolved. So if it's in suspended form, the algae can't really use it. But sometimes certain conditions might change, like the pH might change, or the temperature might change, or light might degrade these solids. Then the phosphorus becomes dissolved, and hence it can once again lead to algal bloom. So I would not use algal bloom as a complete indicator for phosphorus check. It is certainly one of the first levels of indication. But as we like to say it here in our research center, you are never sure unless you measure. I mean,
Yes.
I would like to use an analogy here, if I may. Some of my
Please.
colleagues are working with sugarcane ripening, and sugarcane, as there is a small time when you have to harvest when the sucrose levels are really high.
High.
If you harvest it either side of it, the sucrose level goes down.
Goes down.
And the farmers don't get that profit. So historically, what the farmers have been doing, I heard, is that they just bang the sugarcane. They take one of the samples, bang it on the wall or bang it on the, then they hear the sound, and then they can judge that. And that we can't question that, it's been passed on through tradition. So we don't question that. But those times are gone, and now we have sensors, we have drones, so we can really monitor everything at an accurate level. So we don't need to rely anymore just on, observations, which we did. So it could be used as a first line of check. But to verify, we are coming at an age where, things are becoming cheaper. Sensors are becoming cheaper. The same thing goes for water quality as well. It's a bit easier to analyze the water samples here, and phosphorus and nitrogen should be one of the basic parameters that should be
They're
tested.
the leading, no? When we
Yes.
talk about wastewater treatment.
Exactly. So I would say that's the best way to be sure is to, test it frequently. That's how.
Okay, wonderful. So I have questions like ocean and sea, but North Sea of our Netherlands, where everything eventually flushes out, because we know that in Netherlands, it's like a chain or a series of canals which are opening up to the sea, but of course controlled through the dikes. So I leave you with this question and then hand it over to Ekta. What happens to these eutrophicated water when, because in Netherlands, we have seen that they are flushing the canals, and I'm assuming that everything eventually lands up in the North Sea, as we call them. What is the marine ecology very, susceptible to the presence of phosphate, or how do they deal with this kind of pollution reaching? Because ocean pollution or marine pollution itself is a vast subject which we should not discuss here.
Right.
But it is causing a serious concern. So is phosphate a serious concern even in the sea and ocean?
It is. The Wadden Sea, the North Sea, I have not looked into. I was working on a project.
Friesland.
Yeah, Friesland, right? And so I was working on a project in the Baltic Sea, which, touches a bit of the Scandinavian countries, Poland. And I could easily see satellite images, which could show this, of course, the sea blue color, but then you could see this green, completely covering the sea. So it is a huge problem. Algal bloom is a huge problem in seawater. And one of the sources, there are multiple sources. One is agricultural runoff as well because of, fertilizers. that's a slightly more difficult problem to solve at the control stage. It's better to prevent, usage
Prevent.
because it's a very diffuse source of pollution, right?
Hmm.
Unlike a sewage where it's a point source where you
Hmm.
can specifically target certain areas. So there the idea was to target these point sources, which were like sewage treatment plants or any other effluent
Industries.
treatment plants that use phosphorus, treated. For agriculture, the idea was to prevent it at the spray level,
Source.
irrigation level, and the fertilizer usage level. So to answer your question, yes, it is a challenge. They are looking into it, but it is still a challenge in certain parts. And the way forward is to use a combination of prevention is always better wherever
Always
we
the
can do
better
this.
option.
And in some areas, it's easier to do it at the preventive stage, and other areas control can still work. But if you can manage to prevent, it at the source,
That's the best option any day. Any day.
nothing like it.
Thank you so much for taking those naive questions, because at Friday Waters, we are really trying to develop citizen science to bring these difficult subjects in a very simple layperson language. And I was the devil's advocate for the day. Thank you so much, Prashant, for being so patient and answering my questions. And over to you, Ekta. Thank you.
Thank you, Mansi.
Thank you, Mansi. It was really interesting to hear both of you. And first of all, thank you, Prashant. You reminded me the whole chemistry, physics, and maths, and my school and college time. And when
I hope in a good
read
way.
your topic, sorry.
I hope it was in a good way and not in a scary way or something. When people are reminded about the school science and
Yeah, seriously. So, those chemistry, physics textbooks, that how this surface area volumes, how to increase the volume and have the good effects and all these things. So, is there any disturbance, background noise?
no.
No?
No, it's okay. Okay. So, as we always say that waste is waste till we don't use it.
Yes.
So we have, yes. So everything is useful, and we have to see that how we can use it. We can reduce this waste and then reuse it. So only then we can be successful. And also it's a very good learning that, we all want everything, but we don't want to do anything. So we are focusing on only the short-term benefits. There are no right now we have water. We can dig the wells and all and take out the water. All these farmers, and even not for the home use also. We
Right.
just go for the boring, tube wells and all. But we never think about the alternate resources. So it's time that we should focus on these pollutants and how these pollutants can be made useful, extracted, and the clean water can be available for all. So that's what I learned, and time to go back to the textbooks from the school. Yeah, so that those textbooks needs to be reminded again to all these middle generation as well as the students, that we have to make them understand that whatever mistakes we generation did, they should not do that.
Yeah. Certainly, it's all about
So this
learning
is
from our
the
mistakes, right?
Yeah, that's a wonderful learning. And now it's time for a quick announcement for the next sessions. Please join us for the next Friday water session. We invite you to Water Arts on September 29th, 5 p.m. IST with Aslam Sayyed on the Bhishtis of Mumbai. So link to join the session is in our chat box. And for the upcoming sessions and regular updates, follow our social media links. Also visit our website w4w.in. And also never forget to join us for the thesis sessions on every third Friday of the month. So thank you, Dr. Prashant. Thanks for this wonderful session, and looking forward to have more sessions and good collaborations with you.